Welcome to CMOS RF integrated circuits. Today's lecture is about transmission lines, as we were talking about in the previous class. This is all part of the third module, that is passive components. Now, in the previous class what we developed, we started with a piece of wire and developed a model for the wire. Now, we noticed that the wire had a little bit of inductance per unit length, little bit of capacitance per unit length, some resistance per unit length, probably hopefully not some conductance per unit length, and we cascaded these small units and made the complete wire. And then we were trying to do the business of analyzing how a voltage or a current propagates through this wire, and we came up with a couple of differential equations. 1 and 2 were the two partial differential equations that we started from, and we modified these partial differential equations. We came up with 3 and 4, I am sorry, we came up with these two, let us call this 5 and 6, which are my final partial differential equations, just that these two differential equations are not they are no longer coupled to each other, they are independent of each other now. So, I have got voltage, all voltages, and I have got current, all currents, right. You have to remember that eventually the voltage and the current are indeed related, but not an issue right now. Then we notice that the solution to this is basically the wave equation. You have got a forward moving wave, a backward moving wave. If I have the resistance and or the conductance to be non-zero, then it creates an attenuating wave. So, there is a wave which attenuates over time, right. That is what we finally came up with. Now, just for this particular lecture, let us assume that R is 0, G is 0. So, in that case my transmission line basically looks like this. Okay. That is my basic transmission line, and then you solve those equations that we worked on yesterday, and you end up with just these portions. Basically, I and V have the same relationship as a function of x and a function of time. So, they have the same solution. The solution happens to be the wave equation. This is the wave equation. The solution to the wave equation is something like this. Okay, there is a forward moving wave and there is a backward moving wave. V plus is my forward moving wave, V minus is my backward moving wave. All right, what about the current? The current is also going to have a very similar relationship. but this I plus and I minus are basically different from V plus and V minus. They can be anything. Okay. Now, what is the relationship between the voltage and the current? That was our intermediate equation or original equation that we discarded. You remember equation 1 and 2. We discarded equations 1 and 2 early on, because they were coupled to each other, right. But this is what is going to tell us the relationship between V and I. So, these two relationships need to be added into my expressions for V and I, and dou V by dou x, if I look at this as my solution for V, dou V by dou x is going to become equal to the derivative of V plus the derivative of V minus, right. What about dou I by dou t? Dou I by dou t is going to be minus C times the derivative of I plus C times the derivative of I minus. Okay. So, the derivative of V plus is going to be equal to minus L prime right. This is what happens when I substitute everything. What about the other version? The other version is very similar. So, I get I plus I minus is going to be equal to C times right. Now, I have got two equations. My unknowns are I, let us say my unknowns are I plus and I minus. Let us say I know V plus and V minus. My unknowns are I plus and I minus. Can I figure out the values of I plus and I minus from these two equations? So, surely you can, right. These are two independent equations. You are going to get the values of I plus and I minus, and it turns out that I plus is going to be equal to V plus times So, this is what it turns out, satisfies both of my equations, I plus and I minus. If I choose these as my values, then it is going to satisfy everything. Now, of course, you remember that C is equal to this quantity. This is, we did this in the previous class, right. So, this basically gives us the relationship between the current waves and the voltage waves. So, what have I got so far? I have got a wire. It is not really one wire, it is a pair of wires. And what is going to happen is that if I launch a wave, onto the wire, then this wave is going to go all the way, portion of it is going to reflect back. So, at any given point of time, at any given point in space on the wire on the x axis, in general there are going to be two waves, one going in the forward direction, one going in the backward direction. Okay. So, that is the physical interpretation of the whole story. So, I have got a forward moving wave, a backward moving wave, and these forward and backward moving waves are both voltage and current waves. The voltage forward moving wave is equal to the current forward moving wave times square root of L by C, that is Z naught, remember. Okay. And the current backwards moving wave is negative of the voltage backwards moving wave divided by Z naught. So, this is what I have. Okay. Here V plus and V minus are functions of x plus C t and x minus C t. So, this is my general solution to the transmission line problem. Of course, this is a special version where I have ignored the presence of resistance and conductance. When the resistance and conductance are present, like in the previous lecture we discussed, we will use the phasor notation, because it is better to use the phasor, it is going to be easier for us when we use the phasor notation. We are going to assume that all of these are sum of sinusoids. We are going to break up any signal into its composition in terms of sinusoids, and we are going to treat each sinusoid one at a time, right. Each sinusoid is going to create a forward and backward moving wave, which is slowly being attenuated by this factor sigma. That was my solution in the previous class. We did this, I think we did this quite thoroughly in the previous class. So, there also you basically are going to end up with more or less the same solution, just that now Z naught is going to be a complex number. So, in general Z naught, you can show that Z naught is going to be equal to square root of this quantity. Okay. So, you pick the frequency Z naught, you have to compute your Z naught for that particular frequency. Otherwise, there is not much to be changed in these set of equations. It is just that now V plus V minus, these are going to be phasors that we are going to talk about. V and I are also going to be phasors that we are going to talk about. So, they already have e power j omega t built into them, they are already sinusoids. So, if I have a sinusoid voltage, if I launch a sinusoid voltage, then a portion of that sinusoid voltage is going to reflect back from the load, etc. Now, this derivation, this set of derivations I needed to do to relate back to what we jump started earlier. How did we jump start in the earlier in our introduction? We had jump started on this business of reflections, right. What did we say? We said that I have a wire, this is a transmission line of characteristic impedance Z naught. Now, you see what is Z naught? Z naught is not a resistance. Okay. This is called the characteristic impedance. Z naught is a mathematical entity, it is not a resistance at all. If you have R and G equal to 0, then Z naught is going to be square root of L by C, L prime by C prime. Right. In any case, the real part of Z naught can be approximated to this quantity. As an engineer, you do back of the envelope computations and you can approximate the real part of Z naught to this particular quantity. Fine. So, what is going to happen? I apply, let us say, a step, okay, from 0 to 1 volt. Let us say my source resistance is 50 ohms and let us say Z naught is 200 ohms and let us say my load is 50 ohms, some random numbers, right. What is going to happen? First, what needs to happen is you need Kirchhoff's laws to be satisfied everywhere. So, I need Kirchhoff's laws here, I need Kirchhoff's law here. Right. So, Kirchhoff's law is going to tell me that the potential on the source side of the transmission line V s is going to be equal to 1 volt, let us say V volts, minus I s times R s. Okay. This is what Kirchhoff's law is going to tell me at the source side. Remember, Kirchhoff's law is always satisfied, no matter how hard you try, it is very difficult not to satisfy Kirchhoff's law. In fact, if a physics person claims to you that Maxwell has an extra term which makes Kirchhoff's law not being satisfied, say that it is still called a displacement current. So, if you call it a displacement current, that extra term in Maxwell's equations, Kirchhoff's laws is once again going to be satisfied. So, anyway, Kirchhoff's law, it is very hard not to satisfy Kirchhoff's law, and even inside the transmission line Kirchhoff's law is going to be satisfied. All that you need to realize is that the transmission line is not a wire, there are paths, leakage paths all over the place. So, portion of the current can come out. So, Is is not going to be equal to Il, and that is not a violation of Kirchhoff's law. Okay. So, we have got these two as our basic starting points. First, that the voltage across the load is IL times RL, voltage Vs is going to be V minus Is times Rs, right. Then we realize that Is, first of all, Vs at the beginning of the transmission line is going to be equal to a forward moving wave plus a backward moving wave. Okay. And similarly, Is is going to be a forward moving wave plus a backward moving wave, right. So, if you understand this, then suppose this is a pulse waveform, what is the backward moving wave initially? You have just applied the pulse, everything was static before this, there is no knowledge to the circuit that you are going to apply the pulse in future, right. So, nothing is coming backwards, you are about to apply the pulse, nothing is coming backwards. So, there is no backward moving wave initially. Initially when you launch your wave, there is no backward moving wave, you just launch it. So, V minus initially is 0, right. So, you only have a forward moving wave. In that case, you have got Vs is equal to V plus, that is V plus is equal to V minus Is, which is V plus by Z naught times Rs. So, what is V plus going to be equal to? Okay, verify this for yourself. All right. So, you basically have to put all the V pluses together and solve the simple equation, and you will get V plus to be equal to V times Z naught by Rs plus Z naught. So, it is almost as if you have got a voltage source V with Rs and you are launching it onto a resistor of value Z naught. Just that it is not really a resistor. So, be very careful here, it is not really a resistor, it is a wire, launching it onto the wire, but initially the wire is looking like its characteristic impedance, because there is no backward moving wave. So, at that initial instant of time there is no backward moving wave. So, this is what you get. So, now I know the value of V plus. Okay. So, V plus is a pulse of value V by Z naught, I am sorry, this is the value of V plus, it is a pulse and it is travelling along the wire in the forward direction. And similarly, there is a current wave also which is travelling along the wire in the forward direction. Now, what is going to happen? It is going to hit the load. Okay. Now, on the load, the voltage is equal to the current times the resistance, the load resistance. This is coming directly from Kirchhoff's law. This voltage at the load is going to be in general equal to V plus V minus, forward moving wave plus a backward moving wave, and the current is going to be equal to the sum of a forward moving current and a backward moving current. Agreed? I know the value of V plus already. What should the value of V minus be? So, it is a simple matter of doing a couple of transpositions, and so what you are going to find out is V times Z naught minus R L by R S plus Z naught right. Something of this fashion. So, what does this tell you? What is V plus, what is V minus by V plus? If a wave of size V plus hits you, if a wave of size V plus hits you, it is going to create a reverse moving wave of size V minus. What is the value of V minus? It is going to be V plus times R L minus Z naught by R L plus Z naught. So, this quantity is the reflection coefficient. Okay, also known as gamma. Okay, we used this formula before. Earlier on in the first lecture, we used this formula and jump started the whole discussion, right. However, this is the way it comes out. Okay. So, now this V minus wave goes and hits the source yet again. Right. When I hit the source with V minus, V plus is already there, right. V plus was the result of this source, of the voltage source. When I created the voltage source, when I applied the voltage source at first, it created a positive moving waveform called V plus. Okay. That voltage is still around. So, V minus adds on to that voltage. The new wave which is moving backwards adds on to the old wave. The old wave is still present over there, right. So, if you use superposition, you can use superposition. If you do use superposition, then you can ignore the fact that V plus was there, you can ignore the fact that I launched a wave to start with, and you can just consider the fact that you have got V minus, a wave is coming backwards, it hits R s, and then what is going to happen? It is the same situation as before, the one we just computed. You are going to get a new forward moving wave, which is going to add on to the old one, right. So, you will get another reflection over there, it is going to add on to the old one, you are going to get a new V plus, extra bit of V plus you are going to get, right. So, eventually the waveform V plus is going to look like this, you will get a lot of steps in V plus. So, you have got, so as a function of time, if I just look at the value of V plus, initially V plus is something, and then after double the transit time V plus is going to change a little bit, after 4 times the transit time V plus is going to change a little bit. V plus itself is going to change if you think about it, right, if you do not think about the superposition. If you do think about superposition, then every time you are getting gamma times the old wave, but then you have to add up all the past history. Okay. So, that is why we have a reflection coefficient on the source side. Reflection coefficient on the source side, you just replace R L by R s, and you will get R s minus Z naught by R s plus Z naught. This is going to be the reflection coefficient on the source side, right. So, how are we going to tackle this final example? Suppose it takes me 1 second to travel from the source to the load. Suppose R s is 50 ohms, R L is 50 ohms, and suppose Z naught is 200 ohms. This is what we started with, and suppose I launch a 1 volt wave. So, when I launch a 1 volt wave, this 1 volt wave sees a source resistance of 50 ohms, it sees a characteristic impedance of 200 ohms. So, what is the portion that reaches the wire? The portion that reaches the wire is 4/5 of 1 volt. So, you are basically launching V plus of value 0.8 volts. Now, this is how we draw it. This V plus, wave V plus propagates over the wire, it hits the load after its transit time, whatever it is, 1 second. 1 second later it hits the load, 0.8 volts hits the load, and then a portion of it reflects back, gamma times 0.8 reflects back. So, instantaneously you get a V minus launched, right, and the value of that V minus is going to be, what is your gamma? Gamma is minus 0.6. Okay. So, instantaneously minus 0.6 times 0.8. So, minus 0.48 volts gets launched backwards. And this is your V minus, which is propagating all over the wire. So, at any point of time, if you want to compute the voltage at any distance, let us say you want to figure out the value of the voltage at this point on the wire. So, you go over there and you keep adding up these voltages, and that is how the voltage is going to change. So, all of these are superposed on each other. So, at this time it is 0 volts, then at this time it is 0.8 volts, then at this time it is 0.8 plus minus 0.48 volts, which is 0.32 volts, right, and so on. So, this minus 0.48 volts hits the source, and once again gamma is minus 0.6. So, minus 0.48 times minus 0.6 is going to be how much is it? It is about plus 0.3 or so. Yeah, it is about plus 0.3 or so, I do not know the exact value. So, I will now have another forward moving wave, which is plus 0.3 volts. Okay. And now, this 0.3 volts is going to hit the load, and it is again going to reflect back 0.3 times minus 0.6. So, you get minus 0.2 volts going backwards, and so on and so forth. This keeps going, happening back and forth, back and forth. And finally, if you look as time tends to infinity, what should be the voltage at the load? Common sense. As time t tends to infinity, steady state, all the capacitors are open circuits, all the inductors are short circuits. So, the wire is really a short circuit. What does that mean? That means that you have got RS, you have got RL, right. So, you should be getting appropriate voltage division, you should be getting the right voltage at the output as time tends to infinity. So, your calculations should go towards that always, your calculations should eventually settle, unless you have done something dramatic, right. If your resistance is negative or some dramatic mistake is there, your calculations should always settle to the final desired value. And so, as you see, you have got 0.8 to start with. The target was 0.5 to reach the load. You transmitted 1 volt, 50 ohms was the source resistance, 50 ohms was the load resistance. So, you expected 0.5 volts to reach the load. So, you started with 0.8, then after some time you got 0.8 minus 0.48, so 0.32. Then after some time you got a further plus 0.3, so you got 0.62. After some more time you got a further minus 0.18. So, that adds up to 0.44. You see, we are slowly zooming towards the correct value, which is 0.5 as time progresses. Now, the more the mismatch between the source load and the Z naught, the longer it is going to take for this to settle down. And you also see that you transmitted a pulse instead of receiving a pulse. What after some time, what you received you first got 0.32 volts at the load, then it jumped to 0.62 volts, then it came down to 0.44 volts, then presumably it is going to go to point something closer to 0.5 and so on. So, this is what you are going to end up with, right. So, therefore, it is important, just for purpose of fidelity, you transmit a pulse, you should receive a pulse. So, just for that purpose, it is important for us to make sure that the source and the load are matched to each other, and this is where the whole topic of matching is going to arise, and we have already discussed L match, pi match, all of those different matching networks we have already discussed. Note that those are matching at a given frequency. Okay. Here we are talking about a broadband pulse. So, this is never really going to work, even in spite of the L match etc. This broadband pulse is never really going to be faithfully reproduced, unless I really have resistors over there. Right. So, what have we got so far in our discussion? We have kind of understood the, not kind of, we went into thorough detail, we solved all the equations, we understood the transmission line, we understood the fact that what is going on is because the transmission line is a distributed network, there are leakage paths. If I launch current I in from the source, I is not going to reach the load, some of it is going to leak out through the capacitors, through the conductances. Similarly, if I put a voltage V across the transmission line on the source side, I am not necessarily going to see V on the load side, some of that voltage is going to drop across the inductors or across the resistors, right. That is number 1, that is what we saw. Then we solved the equations for the transmission line. We took a special case when I have only got inductance and capacitance. This is the lossless situation. The lossy situation is just a little worse than this. Okay. That also we can solve. Unfortunately, we can solve that only when we talk about sinusoids. When I launch a sinusoid, I can solve it. When I launch something more complicated than sinusoid, then I will have to break up the more complicated signal into a sum of different sinusoids. Sum could also be an integral. So, I have to do the Fourier transform of the sinusoid to get its representation in terms of sinusoids, and then for each sinusoid I have to work out what happens, right. For each sinusoid in general, the reflection I am sorry the characteristic impedance is going to be different. Where did I write that? Yes, for each frequency the characteristic impedance is different. So, for each frequency the reflection coefficient is also going to be different. So, this is all bad news. The end of the day, you need a computer to figure out everything. Okay. So, if your situation involves some kind of sum of sinusoids, then I suggest that you just simulate it and be done with it. We have good computational techniques that will work everything out for you. If it is just a sinusoid, we can understand with the help of equations what is going to happen. So, we end up basically with the same equations as the lossless case. Where are those equations? Yeah. So, we end up basically with the same equations. Let me just write them out again. So, the phasor V is now going to be and the phasor I is now going to be okay. However, when I say phasor, it really means that I need to multiply this by a factor of e power j omega t. Okay. So, at a frequency omega, this is what is going to happen, and here z naught is that complicated expression. Something like this. C is not exactly going to be the speed of light, but almost the same quantity. It is going to be almost the speed of light, not exactly. So, c can still be approximated as the speed of light. So, okay. So, what will this mean for us? This will basically mean that as I progress over space, I am also going to get attenuation. That is the only difference. So, what we did in the previous class, let me just remind you. So, this was my final solution to the equation, and we said that we can say that voltage is e power sigma plus j omega x times e power j omega t, and then I find out the values of sigma and j omega by taking the appropriate square root, and then I build up my function. So, what is basically going to happen is that as you progress over space, you are going to get attenuation. So, you start off with a sinusoid on the load side. As you progress over the transmission line, you are going to get attenuation, because there is resistance. As far as voltage is concerned, there is resistance. If you think about current, then there is conductance, which provides a leakage path, and as a result the magnitude of the current is going to decrease. Okay. So, we are going to summarize the entire module with this. In this module, we first started with resistors, then we worked on capacitors, and then we worked on inductors, and after that we worked on transmission lines or wires rather. So, under resistors we just discussed the units. Ohms per square was the unit, and if a surface resistivity is given to you, you can figure out by counting the number of squares in the track what is the resistance of the track. That is, as far as resistance goes, it is easy. Capacitance. Capacitance is very easy to think of. All you need is two parallel plates. So, you have got two plates, you have got a capacitor. Now, A epsilon by d, this age old formula that you probably remember from your high school days, it is a very good formula. It usually works, but keep in mind that this formula was built for infinite plates, infinitely large plates. So, when you restrict the size of the plates, which is usually the case, then you not only have to account for A epsilon by d, you also have to account for fringe effects between the two plates. This fringing is going to happen along the perimeter of the plate. Also, the thicker the plate, the more fringing. So, these are my field lines. So, thicker the plates, more fringing. Fringing is going to happen along the perimeter. So, as a result, if I want to just look at the fringe capacitance, then the fringe capacitance is proportional to the perimeter, it is also proportional to the thickness of the plates. Then we talked about inductors. Oh, we talked about different ways to make capacitors. Then we talked about inductors. What were the different non-idealities in inductors, core losses. Then we talked about copper. First we talked about copper losses, then we talked about core losses or eddy current losses. We figured out how the eddy currents are pooling and what is the exact mechanism. Then we also talked about parasitic capacitance, as a result of which you are going to get a finite resonant frequency for the inductor, beyond which the inductor will start looking like a capacitor. Then we further went and studied wires. We talked about skin depth, then we talked about wires having inductance, capacitance, resistance, and then we developed a model for transmission lines. So, with this I am going to close this chapter, and in the next class we are going to talk about new things. Thank you.